So today is a strange lecture. What I want to do is I want to do enough of the advanced theory so you see what you need to do to make these subjects rigorous without doing so much that everybody drops the class. Okay? What class would you need to take to make this truly rigorous? Real analysis. So for those of you who had me in multivariable calculus, where the answer was almost always linear algebra, now the answer is almost always real analysis. If it's not real analysis, guess complex analysis when you need even more. So what I want to do is I want to talk a little bit about the notation, a little bit about the technical issues, a little bit about maybe how we try to resolve them, and then give you a sense of what you really need to do to make things rigorous and how easy it is to fall into mistakes. So we already did one example last time of something that seemed reasonable but led us to a contradiction. So what was it that we did last time? Yes? Russell's paradox. So sets are more complicated than we expect. You can't just collect a bunch of things together that have the same property. And as soon as we have this revelation, we now have to be very cautious about any new mathematics we do. We have to be very careful. What objects are we looking at, and how are we combining them? What are we acting on them with? Okay, so I want to start off. We've already done Russell's paradox. I'll talk a little bit about the Banach-Tarski paradox later today. What it says is if you have a solid sphere, let's say it's a sphere of gold to make it fun, you can chop this sphere up into 5 pieces, and you can move them apart. If I translate a piece, does it change its volume? If I rotate a piece, does it change its volume? So you can take 3 of these pieces and rotate and translate them away and combine them and get a solid sphere of exactly the same radius with no gaps. And the other 2 pieces that are left over, you can also rotate and translate them and combine them and get a solid sphere. So you can double the gold sphere. And of course, if you can do it once, you can do it n times. You can make as much money as you want. There's some issues with this for practical purposes. You need to do what's called you need to use an unmeasurable set to do this. These are sets that are so bad we can't really describe them in a physical way that you can understand. And the existence of these sets rely on something called the axiom of choice. And so depending on whether or not you believe in the axiom of choice, these sets either exist or do not exist in your language of discourse. We really don't want to be able to chop up a set into 5 disjoint pieces and just by rotating and translating them have an issue like this. We'd like to believe that volume is preserved under rotation. Volume is preserved under translation. These are assumptions. These are axioms, and you have to then say, what are the consequences of these axioms? How do they interact with other axioms? For any senior who's looking for a really good level theory math colloquium, the Banach-Tarski paradox is an excellent, excellent example. All right, so what is the axiom of choice? Axiom of choice. Given any collection of sets can form a set containing an element from each. This does not seem like an unreasonable assumption. I give you a set of sets, I give you a collection of sets, just choose one element from each and put that together and make that a set. I don't like this axiom. Yes?
What about empty set? Is like any collection of like...
Well, so let's say non-empty sets. We'll say non-empty sets. This doesn't sound that unreasonable. The difficulty is how do you choose your element from each set? We don't necessarily have an ordered set. We don't necessarily have a first element, a second element. Imagine this set is all people in the world, or maybe all people on college campuses. I'm assuming everybody is wearing some kind of footwear. Okay? If you assume that everybody in the world is wearing footwear at this moment, can you give me a way to get an element from each?
So it could be like flip-flops versus closed, like open-toed versus closed-toed shoes. Those are like 2 sets.
Right, but so I'm looking at each person. I'm looking at, say, all the clothing and the footwear and all the accessories on each person.
Take everyone's right shoe.
Take everyone's right shoe. And if you don't want to take everyone's right shoe, what could you have done? The left shoe. Something really nice and clear, a very nice rule. Take all the right shoes, take all the left shoes. So if you have a collection of sets where you have something like that, it's no problem. The difficulty in all of mathematics is with infinities. So it's problems with infinities. And depending on what classes you've taken, your professors may have glossed over the difficulties that arise whenever the infinite enters. There's some mathematicians who actually do not like to work with the infinite. They want everything to be finite. And in some sense, when you consider what you're able to work with physically, it's not horrible. It is very convenient to have infinities. If you've done integration, you might remember the improper integrals, where you go all the way off to infinity, and how you have to be very careful to make sure things converge. What I don't like about this assumption, this axiom, is it gives too much power to mathematicians. I know normally you would think a math professor would actually like something like that. I think this gives us too much power. I am fine with something that's called the countable axiom of choice, where the only difference is it's giving any countable collection. So I want to talk a little bit about countable versus uncountable today. If you take a set theory class or a real analysis class, you'll do a lot more on this. But I want to get you aware of the issues and what we have to do around it. So a set is countable if there is a one-to-one correspondence with the positive integers. So a nice way of saying it then is I could write my set x1, x2, x3, x4. It gives me a way to index my elements. Really good examples, the non-negative numbers. Another good example are the integers. -2, -1, 0, 1, 2. Well, looking at it like this, it's not clear that this is in a one-to-one correspondence with the integers. What we could do, however, is we could write the set as 0, 1, -1, 2, -2, 3, -3. And then this would be the element x1, x2, x3, x4, x5, and so on. And so this gives us a one-to-one correspondence between our set and the positive integers. Frequently, we want to have a little flexibility. I may not want to have my first index be 1. For this problem, what would I want my first index to be? 0. So really, we'll say a set is countable if there's a one-to-one correspondence with either the positive integers or the non-negative integers. And so I might want to do y0, y1, y2, y3, something like that. If you do a little bit of work, you can show that the rationals, which is the set of all p over q, p, q are integers, q does not equal 0, you can show that this is countable. All right, I'm not going to go into too much of this. We really don't need that for this class. I see at least one person doing like a spiral around. That's a very good way of doing it. What do you think at most countable means? So if I tell you a set is at most countable, what would you guess? Yes?
It's either finite.
Excellent. It's either finite or countable. All right? So what we're going to do now is we're going to play the games of different orders of infinity. Okay. So now we're going to get rid of the axiom of choice right now. So a set is at most countable if it's either finite or there's a one-to-one correspondence. So give me a set of size 0. Yes, the empty set. So I was a postdoc for a year at the Ohio State University, not at a Ohio State University. Right? This is one of the times in mathematics D is correct. There is one empty set. There are not two different empty sets. There are not two different sets that have no elements. There is a empty set. So a set of size 1, the set containing the empty set. The set containing Lenny. Right, those would both be examples, okay? Set of size 2, Lenny and, no, not George. I'm sorry? No. Nobody knows who should go with Lenny? Carl. How many people know why Lenny and Carl go together? I'm sorry?
Marxism?
No, 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 no. That'd be Carl with a K. All right, so I'm sure you'll be able to find this if you Google. It's interesting to just see how pop culture changes. All right,
Are they the friends from The Simpsons?
Yes, they are the friends from The Simpsons. There's a very small difference between the two of them. I'm sorry?
Sorry, my bad.
Okay, so we have sets of size 1, size 2. Generating a finite set is no problem. Set of infinite size. Natural numbers. Say 0, 1, 2, 3. Another one is the real numbers. Okay? These are both infinite sets. And so the question is, are they the same size infinity? Yes?
No, they're not, because or is like you can find something in intervals.
Mm-hmm.
So it's an interval. It's like the interval between the interval two numbers in n sub infinite.
Well, you've got to be careful because the rationals are countable, and there's always infinitely many rationals between any two reals.
You can put it on a one-to-one correspondence, because you can put m over n.
Right. So you are correct that the reals are a higher infinity than the naturals. And the reals are uncountable, the natural numbers are countable. I don't want to go into too much detail. I want to just give you a flavor for what goes on. So there's something called the power set. So the power set of a set A is all subsets of A. So for example, if A is just the set containing x and y, the power set of A is what are the possible elements of the power set of A? I want all subsets, yes.
The empty set.
The empty set, perfect.
The set containing x, the set containing y, the set containing...
And so what we see here is that the power set, if my set had 2 elements, the power set has 2 squared. If I had 3 elements, x, y, z, I would have to add a z here. I would have xy, xz, yz, and then xyz. And so what you would see is this has 3 elements. The power set has 2 to the 3 elements. Think of it, for each element, you have a choice. You either take it or don't take it when you're forming a subset. So when you're creating a subset, you have 2 choices at the element x, 2 choices at the element y, 2 choices at the element z. You have 2 times 2 times 2 is 8 choices. Okay? So the cardinality of a power set is going to be 2 to the cardinality of your original set. I'm not going to prove that theorem. It is a nice result. And so we often let A, or the cardinality of A, be the size or the number of elements of A. And then the claim is that the cardinality of the power set of A is just 2 to the number of elements of A. In particular, this is clearly greater than the number of A if this is finite. Right? If A it has only finitely many elements, 2 to any number is just larger than that number. You know, prove that if you want as a little warm-up exercise. The amazing fact is that this still holds when you have infinite sets. So the cardinality increases. So notation, this is one of the few times it's useful to be Jewish, Aleph naught is equal to the cardinality of, well, I guess we'll use the natural numbers. So Aleph naught is the smallest infinity. Now we have the reals. It turns out the reals is equal to 2 to the cardinality of the integers. The way to look at this is if I give you a real number, look at its binary expansion. For its binary expansion, each digit is a 0 or a 1. So you have infinitely many choices. At each choice, you have 2 possibilities. That's 2 to the Aleph naught. You have to worry that you have multiple ways of writing some numbers. I don't want to get into those technicalities. I want to give you just a broad overview. Yes?
If there is a smallest infinity, is there a biggest infinity?
No. Because the whole point is you can just keep using the power set. The power set of whatever you had will be larger. So you can make sets as large as you want. So any thoughts as to what the cardinality of the real should be denoted? What would you think? What's one possibility? Yes? Aleph 1, right? Maybe the reals are the next infinity. If it's not Aleph 1, what could it be? Maybe Aleph 2. Maybe Aleph 3. Maybe Aleph sub Aleph naught. So here's, yes? Okay. So here's an interesting question. Is this true? Are the reals the next infinity in size after the natural numbers? Yes? I'm sorry?
What kind of all the different kinds of infinities are countable?
Let me think about that. My feeling is no. I think you can start doing some very strange things. They become very absurd processes. But I know there's a difference between ordinal arithmetic and cardinal arithmetic, where with the ordinals, I think you do get stuck in this countable range. But I think you can generate uncountably many infinities by just putting on different things here. So the continuum hypothesis and this goes back to Cantor, is that the cardinality of the reals is Aleph 1. That it's the next infinity. It turns out that the continuum hypothesis is independent of the other axioms of set theory. You can either assume it's true or you can assume its negation. And so we have a whole theory, it's called the Zermelo-Fraenkel axioms of set theory. So we normally say ZF for Zermelo-Fraenkel. If you assume the axiom of choice, it's ZF plus Z, Zermelo-Fraenkel with choice added. And the continuum hypothesis is independent of those assumptions as to whether or not this is the next infinity. It doesn't really matter for what we're doing if this is the next infinity or not, but you might find it fascinating to ponder what are the possible sizes of sets. Is there a set of intermediate complexity? So in operations research this morning, I was talking about fractals. And in fractals, you actually can have dimensions strictly between 1 and 2, or strictly between 0 and 1. And in fact, you have a whole slew of possibilities that happen there. And you can ask similar questions, what happens here? Okay? So again, the whole point is I want you to get just a rough sense of what's out there, to be aware of some interesting mathematics. Yes?
Does the power set of the set of natural numbers have the same cardinality of 3?
Yes. 2 to the Aleph naught is equal to the cardinality of the reals. So we do know, we don't know if that's true, but we do know that 2 to the Aleph naught is the cardinality of the reals. That we do know. And so the final mathematician who finished proving that the continuum hypothesis was independent of the rest of set theory is one of my mathematical grandfathers, Paul Cohen. So I had 2 thesis advisors. On my Princeton side, I go back to Paul Cohen. All right, so we keep track of our genealogies. All right, and the statement is, if your marriage doesn't work out, what can you do? I'm sorry. I was hoping people would say work on it, but okay, divorce, sure. We could do a little bit more extreme. Once you have a PhD advisor, that's your advisor for life. That's your genealogy. I won't ask how many people were thinking divorce, but it is interesting how you can color the answers you want. I feel like Family Feud right now. Okay. So we want to really work on countable sets, not uncountable sets. And the idea is we're trying to come up with a notion of probability. We want to assign probabilities to events. But we're not going to be able to assign probabilities to arbitrary collections of items. That's what the Banach-Tarski paradox is basically telling us. Okay? Infinities are strange. And whenever there's an infinity, you have to be careful. So, danger with infinity. I'll do one example. I'll do 2 examples. How many of you have ever heard of the Hilbert Hotel? Hilbert Hotel is wonderful. So it has rooms 1, 2, 3, 4, going off to infinity. All are full, and a guest arrives, and they're rich. What would you like to do? You have a rich guest that arrives, you own a hotel. This is not a hard problem. What do you want to do? Give them a room, right? Well, if you're going to give them a room, you've got to free up a room. And you don't want to piss off the people who are already staying. So how can you squeeze this person in when all the rooms are filled? Move everyone up. So move guest n to room n plus 1. And so if you slide everybody down, you open up a room. And in fact, you could even free up infinitely many rooms at once. Move every guest to twice their room number. And you would free up all the odd rooms. So you could handle countably many guests arriving at the Hilbert Hotel. It's a wonderful place. Okay? Infinities are strange. How many of you remember Fubini's theorem? So I know there's at least one person here who took Calc 3 with me. So how many people remember Fubini's theorem? Oh dear. So this is one of the key results in multivariable calculus. Right? We don't have that many tricks in multivariable calculus. We can change variables, and you may remember the polar coordinates, the spherical coordinates, the cylindrical coordinates, and we can switch the orders of integration. So Fubini's theorem is about switching orders of integration. So basically, when can you say, I don't want to do x and then y, I'm going to do y and then x? When can you do this and have no harm, no foul? Does anybody, is this coming back now? Vaguely? How many people remember switching orders of integration in multivariable calculus? Just that you've done it. Okay. So you have to justify something like that. It is not always possible to justify switching the orders of integration. And what causes issues is infinities. When you're working on infinite spaces, or when you're working on functions whose the integral of their absolute value is infinite, you can have problems. So I'm going to give you an example where you can't switch the orders. Instead of doing a double integral, I'm going to do a double sum. Okay? I'm going to do the sum over n goes from 0 to infinity. The sum m goes from 0 to infinity of a m n versus the sum m goes from 0 to infinity, and the sum n goes from 0 to infinity of a m n. It would probably help to tell you what the sequence is. So here's my point 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, and so on. Here's the point 0, 1, 1, 1, 2, 1, 3, 1, 4, 1. I'll do one more row. 0, 2, 1, 2, 2, 2, 3, 2, 4, 2. And I'm going to go off to infinity in both of these directions. Okay? I'm going to define my terms to be the following. It's going to be plus 1 over here. It's going to be minus 1 over here. And it's going to be 0 for the rest of eternity. Did you have a question in the back? Or? Okay. Then for the next one, it's going to be 0, then plus 1, then minus 1, and then 0 for all eternity. For the next one, it's going to be 0, 0, plus 1, then minus 1, and then 0 for all eternity. Let's do the column sums first. What does each column sum to? 0. So if we sum the columns first, each column sums to 0, and then when we sum across columns, we get infinitely many zeros, which is 0. Let's do the row sum. What does each row sum to? Yes? The first row sums to 1. All the other rows sum to 0. So when you do the row sums, what do you get? You get 1. So here, you would get 0 equals 1. Okay? 0 does not equal 1. We can't just switch the orders. We've got to be careful. Right? This is why we need classes like real analysis. It is very easy to have mistakes like this. It's very easy to think you can just switch the orders. Okay? I'm not going to prove why Fubini's works where it does. That's not the purpose of this class. But I want you to be aware of this. I want you to be aware of what do we need to do to make this subject rigorous. Right? This is the real danger. Okay? So we do need to eventually take a class in real analysis to have a rigorous foundation. We're going to have to restrict what sets we look at, and whenever we have infinities, we're going to have to be very careful. Okay? There we go. That helped it. And I will end with one last bad function. So this one function tells you why real analysis is such a hard subject. I'm going to define f of x to be e to the negative 1 over x squared if x does not equal 0, and 0 if x equals 0. Okay? Let's think about what's going on. There's only one point where this function has issues. Right? As long as we stay away from x equals 0, this function is fine. Well, let's think about what happens if x is really close to 0. Let's think of x as 1 over a million. If x is 1 over a million, then we have 1 over a million squared, which is a million squared. So we have e to the negative million squared. E to the negative million squared is essentially 0. This function is continuous. This function is incredibly continuous. If you were to plot what's going on, it is really flat near the origin. In fact, if you were to calculate the derivatives of this function at the origin, every derivative is 0. Now, I can't just take the derivative of this piece. I have to go back to the definition of the derivative. F of x plus h, well, I'm going to do it at 0, minus f of 0 over h, take the limit as h goes to 0. And you use L'Hopital's rule. And when you do this, at the end of the day, after the algebra settles, you'll get that all the derivatives are 0. What this means is if you were to try to write the Taylor series expansion for the function, all the coefficients are 0. So the Taylor series would just be TF, I'll do T sub f for the Taylor series of f at x is the function that's identically 0. The only point where this agrees with the function is at 0. Well, if you look at the Taylor series is just f of 0 plus f prime of 0 times x plus f double prime of 0 x squared over 2 factorial plus f triple prime of 0 x cubed over 3 factorial, yada, yada, yada. It's not surprising that the Taylor series agrees at the origin. It has to agree at the origin. When x equals 0, everything else vanishes and I have f of 0. What this tells you is this is the only point where they agree, even when I'm using infinitely many terms. This shows you how hard analysis is. This function's Taylor series only describes what's going on at one point. So we would say that the radius of convergence has length 0. Right? So these are some concepts you should have seen in multivariable calculus. One of the reasons I'm doing this right now is for you to get an idea of what prerequisites should you have mastered, what should you review, what should you ask myself and the TAs. There'll be a TA session, for instance, tomorrow night. So the radius of convergence is just one point. Anybody know this Taylor series expansion for cosine? Okay, so if I give you the function 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, what function am I thinking of?
X squared.
Not x squared. Oh, I'm asking you. So I'm thinking of cosine of x plus 1701 f of x, where f of x is my function from before. If you were to calculate the Taylor series of this function, could you distinguish the Taylor series of this function from cosine of x? A Taylor series does not uniquely determine a function. This is horrible. Okay? Later in the course, we're going to get something called the central limit theorem. We're going to say that when you have these really complicated random variables, if you take enough of them together, it's going to converge to something nice. And then rather than dealing with this really messy thing, you can deal with a nice thing instead. This tells us that convergence is very delicate. Okay? All right, so this should be enough of warnings. If people want to see more about Fubini's theorem and how to get around it, there's a video of my son when he was 2 years old about how to justify interchanging orders of summation. It helps to have a magic wand. All right. So let's do probability. That is the course. So omega will be an outcome space. And then what we're going to do is we're going to have something called sigma, which is what's called a sigma algebra. I believe this is section 2.6 in the book. I have not decided how much of this I want to cover. I'm basically going to just see what kind of mood I'm in today. Okay? The sigma algebra is the set of objects where we can assign probabilities. And we'll have some function probability which maps elements in the sigma algebra to probabilities. And probabilities are between 0 and 1. No matter how unlikely something is, it can't have a probability less than 0. No matter how likely something is of happening, it can't have a probability greater than 1. So we want to figure out what kind of objects can we talk about and what kind of probability functions are worth studying. Okay? If your set omega is finite, it's going to be very easy. So often, if omega is finite, we take sigma to be the power set of omega. And we just assign probabilities to all of those things. And one way we can do it is we assign probabilities to each element of omega. So assign a probability to each omega in omega, then the probability of A would be the sum over all omega in A of the probability of omega. This is one way to build a space where we can talk about. So if I have a finite set, say maybe I'm tossing a coin 4 times. Or maybe I'm tossing 4 coins once. I have only finitely many outcomes. I can assign a probability to each of those outcomes. And then I can ask, what's the probability the first toss was ahead and the 4th toss was ahead? And I would just add the probability that the first toss is ahead plus the probability that the 4th toss is ahead. Okay? If things are countable, it turns out that this works as well. Okay? it's sometimes nice to have a wish list for mathematics, okay? I think every kid has a wish list, at certain times of the year, okay? And we're going to create a wish list for probability. Well, before we do a wish list for probability, let's go back to calculus, okay? When you start proving laws in probability, rules of differentiation, what's the first rule you encounter that is not what you might have expected? The first rule that's different. Yes? The product rule. So the derivative of fg should be f prime g prime. Right? This is false, of course, just in case anybody's forgotten their calculus. But if you could choose how calculus worked, if you were controlling the universe, would you choose to define, or would you choose the derivative such that the derivative of a product is the product of the derivatives? The derivative of a quotient is the quotient of the derivatives. Right? We don't have that. What we have is we have the more complicated fg prime is f prime g plus fg prime. Okay, and there's a nice way to prove this. I think I asked you to prove it in a homework problem. It's using a beautiful idea of adding 0. What I want to do is I want to talk about how you could sniff out the formula. And this is going to be extremely useful in the course. When we have a complicated system, when we have a complicated event, can we do some preliminary calculations and get a sense of what the answer should be? So what we want to do is we want to get a sense of what this formula will be, and then we're going to use that same idea later for probability. So consider nice functions. F of x is, say, x cubed. G of x is x to the 5th. And then f of x, g of x would be x to the 8th. I could do more generally, n, m, and n plus m. Let's just use specific numbers. We can calculate, let's call this function a of x. A prime of x is just 8 x to the 7. F prime of x is 3x squared. G prime of x is 5x to the 4th. And so we can see immediately a prime does not equal f prime g prime. So just by doing this simple calculation, we know the derivative of a product is not the product of the derivatives. It is very hard for me to do this part of the lecture with a straight face because you all know the answer. So imagine you didn't know the answer for the product formula. We see we have an x to the 7. And so the question is, how could we get an x to the 7? Well, I have an x cubed, x squared, x to the 5th, x to the 4th. Oh, these two give me an x to the 7. And these two give me an x to the 7. And if I combine them, I'll get 5 plus 3, which is 8. And so this leads to the guess that a prime is f prime g plus fg prime. It's not a proof, but it strongly suggests what the correct functional form should be. Okay, this is something you want to become very familiar with. Okay? So far, so good? We'll do one more thing that's probably been glossed over in your calculus class. So, derivatives of sums. This is one of my favorite rules. What's the derivative of f plus g? Good. The derivative of a sum is the sum of the derivatives. How many of you vaguely remember some teacher droning on and proving that in class many, many years ago? They should have proved that. Okay? If not, you should prove that, especially if you want to be a math major and move on to real analysis. What about f plus g plus h prime? What should that be? Yes?
F prime plus g prime.
Good, f prime plus g prime plus h prime. The proof uses what's called the method of grouping. And so what we get is we get f plus g plus h prime. Do we agree that that's the same as this? Now we can use the derivative of a sum as the sum of the derivatives, and this is the derivative of f plus g plus the derivative of h. And now we can use this again and get the derivative of f plus g is f prime plus g prime plus h prime. I will use the method of grouping numerous times throughout the semester. It's one of my favorite methods. But it's very important to note it must be a finite sum. We do not have it for an infinite sum. The derivative of an infinite sum is not always the infinite sum of the derivatives. It often is, but that's something that has to be proved. Okay? So the whole point is giving you a sense of how would you attack a new problem? What kind of simple tests can you do to build some intuition? What are the dangers? And a great piece of advice is if you see an infinity, there's a danger. You've got to be careful with how you handle infinities. We will be able to handle countable infinities in this class. We will not be able to handle uncountable infinities. So let's go back to our setup here. We've got some set of elements. We have our space. We have a collection of sets where we're going to assign probabilities, and the probabilities are numbers between 0 and 1. And we have to ask ourselves, what would we want on our probability wish list? All right, so probability wish list. Can anybody think of something to put on a probability wish list? Yes?
Probability of omega is 1.
Good. The probability that something happens is 1. And maybe related to that, the probability that nothing happens is 0. Yes?
Should that be a big omega, or should that be some other notation?
That's a big omega.
It's like the probability of the entire outcome space is 1.
Right, but something happens.
That's something or everything? I'm just asking.
Right. So if I talk about the probability of A happening, that means something in A happens.
Okay.
So this is something in omega happens. What else would you want for your probability wish list? Yes?
If you take the probability of 2 introduce user events.
Good. So if A intersects B is empty, then the probability of A union B should be the probability of A plus the probability of B. And for those of you who are greedy, the probability of the union of A alpha should be the sum of the probabilities of the A alpha if disjoint. So I'm not using I'm not using n as my index because I may have an uncountable collection of elements. What I'm saying here is this is a nice wish list. If I have a collection of things that are disjoint, the probability that one of them happens is the sum of the probabilities that each one of them could happen. Does this seem reasonable? Yes. This leads to some problems. Let's imagine, let's go over here. All right. I think I'm okay over here. All right, so let's imagine omega equals 0, 1. And let's let AX be the element x for 0 less than equal to x less than equal to 1. Okay? So what is the union over all x in 0, 1 of AX? What should that equal? So each set AX is a singleton. I take the union of all of them. What should that be? Yes?
Omega.
That should be omega. It should be 0, 1. If our wish list was true, if the probability of the union of the AXs equals the sum of the probability of the AXs, we're in trouble. what should that sum equal? I worked earlier today. Yeah, it's all right. I need some exercise. Okay, so what should this sum equal? That should equal 1. So now the question then becomes, what would the probability of each of these AXs be? Let's say we have the uniform model. So uniform, we want all AX to have the same probability. What value would we have to put in? Yes?
Probability of each one will be 0.
The probability of each one is 0. If the probability was greater than 0, we have infinitely many of them, so it would blow up. But however, if the probability is 0, so we basically get the cardinality of the reals times 0 equals 1. What this tells us is our wish list was too extreme. Okay? We cannot talk about the probability of a union of uncountably many events, splitting it into an uncountable sum. We cannot deal with uncountable sums. So, cannot have uncountable sums. So that's the dangers. We can't have an uncountable sum. So this statement over here, it turns out to be too restrictive. What we should do is lower our expectations. So we now have a countable union. So lower expectations to countable union. Okay? So we're going to make this a little bit more rigorous in the next class. We're going to have Kolmogorov's axioms of probability. But it's nice to get a sense of what you think they might be. There are issues as we take unions and intersections of sets. If we're only dealing with countably many things, we will be okay. If we're dealing with uncountably many things, we get into this strange situation. We have to now figure out what that is. So basically, some type of infinity times 0 equals 1. And whenever you have infinity times 0, this is not defined. What's infinity plus 5? Infinity. What's infinity divided by 5? Infinity. Infinity divided by infinity. Undefined. You don't know which infinity is bigger. So whenever there's an infinity, you've got to be careful. And I'll end with one nice fact. I'll show you that infinity times 0 is sometimes equal to -1. Yes?
But instead of summing, if we just do the integral, then we're fine.
There is no integral.
Yeah, but for the continuous, like for uncountable sets.
So then that's trying to put on a continuous probability distribution. But we've got to be very careful with how we do things. And it comes down to the notion of how do you define the integral. And so the integral that we work with is not necessarily what you've seen before. So I'll end very quickly with infinity times 0 is -1. So if I give you, here's my coordinate axes, and I take two lines. If this line has slope m, does anybody know what the slope of the line perpendicular to it is? Yes? Yes, -1 over m. So if you have two perpendicular lines, if one has slope m, the other has slope -1 over m. So the product of their slopes is -1. If you know polar coordinates, if you write this point as cosine theta, sine theta, and then move theta by 90 degrees, it's a nice exercise to prove this. Well, there's one place where this could break down. If I'm perfectly aligned with the coordinate axes, what's the slope of the y-axis? Infinity. What's the slope of the x-axis? So if you look at the product of the slopes, -1, -1, -1, -1, undefined, -1, -1, -1, -1. How should you define infinity times 0 in this setting? In this setting, it makes sense to define infinity times 0 as -1. So depending on how your limit is being done, you can get different answers. Okay? So this is a good place to stop. This is the really theoretical underpinnings. I'm not going to go too much into open and closed sets and whatnot. I'm going to have you just look at that in the book, and that will give you the terminology you need to understand these various concepts. Okay.